Hey everyone, in this video we're gonna go over chapter 7 exercise questions. Let's start with number 1. Table P9 contains data on food expenditures in hundreds of dollars, annual income in thousands of dollars, and family size for a sample of 10 families. There are a couple questions that we need to answer. Part A, construct a correlation matrix for the 3 variables in table P9. Interpret the correlations in the matrix. B, fit a regression model relating food expenditures to income and family size. Interpret the partial regression coefficients of income and family size. Do they make sense? C, test each of the slope coefficients at the 0.05 significance level. Which independent variables make a contribution to the forecasting of food expenditure? D, perform the F-test. Is the model valid? E, predict the annual food expenditures if the family's annual income is $90,000 with 4 people. Report the prediction interval. F, determine the adjusted R-squared and interpret it. Is the model a good fit? G, compute the variance inflation factors, VIFs, for the independent variables. Is multicollinearity a problem for this data? If so, how might you modify the regression model? All right, so basically this question asks us to run a multiple linear regression model for 3 variables, food expenditure, annual income, and family size. And then we're gonna carry out a couple of checks or steps to verify if the model is good, whether the model is valid, etc. All right, so let's move to Minitab and start working on the question. As of right now, you should be able to see the Minitab I have on my screen. So it shows the 10 families with food expenditure, annual income, and family size. All right. So part A says we need to construct the correlation matrix. To do that, you're going to go to Stat, go to Basic Statistics, and choose Correlation. For the correlation matrix, we want to choose all variables, all 3 of them. Then click OK. We will get the correlation matrix. Of course, the first thing you see is the scatter plot with the coefficients. What will be easier for us is just to move to the bottom of the results and look at the correlation matrix. And we see several numbers here that tells us the correlation coefficient for each pair of the variables. Let's start with the first column. It shows the correlation between the 2 x variables and our y, the dependent variable. As you can tell, both of the correlation coefficients are close to 1, so meaning that these 2 x variables are highly correlated with the dependent variable y, which is a good news. It tells us it makes sense for us to run the multiple linear regression model. However, if you look at the next column here, it shows the correlation between family size and annual income. This correlation coefficient is also very high, suggesting that potentially these 2 x variables are highly correlated. And based on what we learned in chapter 7, this creates the problem called multicollinearity, and there will be consequences out of it. We will explore more when we run the multiple regression model. So basically, the correlation matrix suggests 2 things. Number 1, the x variables are highly correlated with y. Number 2, the 2 x variables are highly correlated with each other. Potentially, there's multicollinearity. So let's move to B, which asks us to fit the model and interpret the coefficients. We're going to go to Stat, pick regression again, and pick fit regression model. Okay, the y variable will be annual food expenditures, and we have 2 continuous predictors, annual income and family size. Okay, then click OK to get the results. So let's see, the regression shows y is equal to 3.52 plus 2.278 times annual income minus 0.041 0.41 times family size. That will give me a question mark that we're going to take a look further when we interpret the coefficient, because the second coefficient is negative. Recall that when we look at the correlation matrix, all of the correlation coefficients are positive, suggesting all variables are positive related to each other. Okay, so let's look at this table here for the coefficients, right? And we need to interpret the partial regression coefficients for both x variables. The first one is annual income. The coefficient is 2.278. So that means when annual income increased by 1 unit, on average, the annual food expenditure will increase by 2.28 units. Now, going back to the original data and the original units, then we can say for every $1,000 increase in annual income, the annual food expenditure will increase by $228 because we're going to need to use 2.28 times 100. So basically, in terms of answering this question, you're going to say when income increases by $1,000, the average increase in annual food expenditure is $228, holding family size constant. And it is very important that you do add the last clause because we do need to hold the other x variable constant, then change one variable at a time. Now moving to the next coefficient, which is family size, that is not what we expected. It is negative 0.41. Technically, we can still interpret this coefficient as the following. We say when family size increased by 1 unit, on average, the food expenditure will decrease by 0.41 unit, holding annual income constant. So again, going back to the original data units, we can say for family size, when family size is increased by 1 person, the average decrease in annual food expenditure is $41, holding annual income constant. Now, apparently there's something going on because we do expect the family size to be positively related to food expenditure. We also saw that in the correlation matrix that shows all the correlation coefficients are positive. The question also asks, do they make sense? Well, actually, it turns out this coefficient doesn't make sense. Intuitively, when family size increases, we need to spend more on food. This is for sure. Furthermore, we're not there yet, but if we look at the t-test coefficient, actually the p-value here is not less than 5%, meaning that this coefficient is not significant. There are two potential issues here. The first one is it shouldn't be negative. It doesn't make sense for family size to be negative related to food expenditure. Number two, we would expect family size to be a very important factor affecting annual food expenditure. However, based on the model here, it's not the case. So apparently we have multicollinearity. Again, we'll explore further, but as of this step, we can already tell that's a problem. Okay, so part C asks us to test each of the slope coefficients. We kind of did that just now. Let's do it formally. And to do that, we're going to perform the individual t-test by looking at the p-values for each of the coefficients. The p-values are given right here. The first p-value is 0.026, that is for annual income. And the second one is 0.749, that is for family size. Okay, so we are basically testing for beta equal to 0, which is the null hypothesis, versus beta different from 0. We're testing the beta for both x variables. Now, since the first p-value is less than 5%, we can tell that the first x variable, annual income, has a significant coefficient, meaning that the corresponding beta is significantly different from 0. That tells us this X variable is highly correlated with Y according to the model, and it is useful in predicting Y. Okay. In terms of the second X variable, family size, as we just discussed, the p-value is not less than 5%, meaning that the corresponding beta, the slope coefficient, is not different from 0. And therefore, family size, according to the model, is not highly correlated with Y, and thus is not useful in predicting Y. And I said according to the model because according to our intuition, we would expect family size to be highly correlated with Y. Part D, perform the F-test. Is the model valid? So for the F-test, we're going to look at this section of the output. And the p-value we're interested for the F-test is given right here. Is the p-value for the regression. And for this one is 0.005, meaning that the model is valid. Okay, the model is valid since p-value is less than 5%. So at least we know that one of the betas will be significant, and one of the X variables is useful in predicting Y. We've already verified annual income is useful in predicting Y in the model. Part E says predict the family's annual food expenditures if the family's annual income is $90,000 with 4 people. Report the prediction interval. So we're gonna go back to stat, regression again, and then this time we're gonna do predict. Since we just estimated the model, we can do the prediction right away. The annual income will be $90,000, but the original data is in thousands of dollars, so we only need to put 90 here. Family size is 4, so we put 4 there and click OK. There we got the prediction. We have the point predictor, which is 206, since the original value is in hundreds of dollars. So this means for this particular family, the predicted annual food expenditure will be $20,600. That does make sense for a family of 4 with annual income of $90,000. The question also asks us to report the prediction interval, which is given here. It ranges from 49 to 364. Given that the original data is measured in hundreds of dollars, this is converted to $4,900 to $36,400. And actually, this interval is quite big. And one reason is actually given within Minitab. Is what the note says here. This denotes an extremely unusual point relative to predictor levels used to fit the model. Now, if we look at the original data ranges from 3 to 11. So that is 3,000 to 11,000. And we are predicting for a value of 90,000. That is way beyond the range of our X variable, right? So in simple linear regression model discussion, actually we talk about this. We said there, when you try to predict, you want to predict within the data range, right? So you like to predict using annual income between 3,000 and 11,000. But if you're predicting for 90,000, that is outside this range, and the prediction may not be valid anymore. So that's a serious problem. And that also tells us, at least partially, the reason why we have such a large prediction interval. So part F says determine the adjusted R-square and interpret it. Is the model a good fit? Adjusted R-square is given in this table right here. So the adjusted R-square is 72.31. It's the number in the middle. And for multiple linear regression model, we look at the adjusted R-square because the original R-square is inflicted by the number of x variables, okay? And the interpretation for the adjusted R-square is the same as before. This tells us 72% of the variation in food expenditures is explained by the model. Or we can tell the reason why food expenditure differs across different families by looking at annual income and family size. Adjusting for the number of x variables. Is the model a good fit? I would say it's not bad. I would say it's an okay fit, right? It's not super good. It's not like 80, 90%, but it's not that bad. Part G says we need to compute the VIFs and identify if multicollinearity is a problem. Actually, we were able to identify that already, but let's take a look at the VIFs, and they are given in this table, the last column right there. Both of the VIF for the two x variables, since there are only two of them, they are highly correlated according to our correlation coefficient matrix. The VIF also shows is 4.02, which is much higher than 1. And that tells us, yes, there's multicollinearity problem. The question asks, how would you modify the regression model? So apparently we need to drop one of these two. I mean, between the two x variables, drop family size, since based on the model we have, family size is not significant. And the other option is to actually run simple linear regression model with each of the x variables. Then look at the R squared and pick the one with a higher R squared. All right, so that's the first question we have. And now we're gonna move to question number 2. The 1991 accounting numbers for Major League Baseball are given in table P24. All figures are in millions of dollars. The numerical variables are gate receipts, media revenue, stadium revenue, total revenue, player cost, operating expenses, operating income, and the last one is franchise value. All right, so we have quite a few variables here. Apparently that is for multiple linear regression. So let's see. Part A says construct a correlation matrix for the variables. From the correlation matrix, can you determine a variable that is likely to be a good predictor of franchise value? So that tells us franchise value is the y variable, and the rest of variables are the x variables. And then also for part A, we need to discuss it. Part B, use stepwise regression to build a model for predicting franchise value using the remaining variables. Use 0.05 for alpha to enter and alpha to remove. Are you surprised at the result? Explain. So the main purpose of this exercise is for us to look at the correlation matrix, kind of to identify the important x variables, and then we use stepwise regression to build the model to systematically select the variables for regression. Okay, let's move to Minitab. So here we go. I've got the data for all the x variables and y variables. I also have the franchise name. So let's start with the correlation matrix. We're gonna go to stat, go to basic statistics, and then pick correlation. And this time, same as before, we're gonna pick all the x variables. We can select and click OK to get the correlation matrix. You will see a bigger matrix this time with a lot of coefficients. But one thing we want to focus is the correlation between all the x variables and the y variable, which is franchise value. Okay, so the way we will look at this correlation matrix to identify that is to look at the last row, which is franchise value, and the rest of the values, 0.655, 0.78, etc., are the correlation coefficients between this y variable and the rest of the x variables. So if you just focus on the last row of the table, we can tell that the highest correlation coefficient is total revenue right here is 0.925, and the next one is 0.78, which is media revenue. And the next one is operating income, which is also 0.797, which is around 7.8. So these three variables we can tell are highly correlated with the Y variable, and they are good predictors. The rest of them are still correlated with franchise value. Stadium revenue is also related. Now the next one, gate receipt, is not bad, 0.655. It's moderate, and operating expenses is also kind of moderate related to franchise value. So overall, I would expect total revenue, operating income, and media revenue will be the important variables. Then the next thing we want to kind of talk about is the correlation among the X variables. I would identify this coefficient 0.867. It's the correlation between operating expenditure and player cost. They are highly correlated. Intuitively, that makes sense because the higher the player cost, the higher your operating expense will be, right? And the next one is, I'll pick this one, 0.792, which is the total revenue versus media revenue, right? So media revenue is part of total revenue, and it seems like it's probably the major driving factor of the total revenue. So let's see. Part B says we need to use stepwise regression to build the model, and the criteria is if 0.05 for variables to move in, and for variables to remove. So let's do regression. Regression again, fit regression model. This time the Y variable will be franchise value, the last variable we see. We're gonna stack the rest of the X variables there. And then don't forget, we're doing stepwise. So we want to click on stepwise. On the drop-down menu on the top, we want to select stepwise, and remember to modify the alpha value here because we're using 0.05. Right, click OK, OK again. Now have the results for the regression. It turns out, kind of surprisingly, the regression model that is eventually determined is a simple linear regression model. Only total revenue were used in the regression. Now, since this is a simple linear regression model, we look at R-square only. 85%, not bad. The F-test is good. The coefficient also highly significant. Everything looked good. I wouldn't be surprised with the result since we've already determined or discussed total revenue is a very important variable. We also identify two other variables that can be useful, but they are not in the model. I would say for potentially a couple of reasons. Maybe there's multicollinearity. Maybe after total revenue is included in the model, the other variables do not pose a significant contribution to the model. So that's why they are not selected. But that's the results using stepwise regression that tells us. All right, so that's question number 2. Now let's move to the last question, number 3. Okay, so here's number 3. It says a taxi company is interested in the relationship between mileage measured in miles per gallon and the age of cars in its fleet. The 12 fleet cars are the same make and size and are in good operating condition as a result of regular maintenance. The company employs both male and female drivers, and it is believed that some of the variability in mileage may be due to difference in driving techniques between two groups of drivers of opposite gender. In fact, other things being equal, women tend to get better mileage than men. Data are generated by randomly assigning the 12 cars to 5 female and 7 male drivers and computing miles per gallon after 300 miles. The data appear in table P11. 3 parts. A, fit the regression model using age of car and gender. B, interpret the least squares coefficients. C, check the residuals to see any assumption violated. All right, so first of all, one comment. I know when reading this question, some of you might be rolling your eyes and saying, that's nonsense, or I don't think that's true. I know to a certain extent, this argument is going on everywhere. Not as far as I know, not just in the United States, but in China, it's the same thing. So the purpose of this exercise is not for you to think about the argument. It's not evidence for the argument. It's just for practice purpose. The purpose of this question in the exercise is for you to practice using dummy variables, because we have gender in the question, which requires dummy variable. It's a categorical variable, include categories, female, male. So let's move to Minitab and perform the analysis and see what we get. There we go. We have three variables: miles per gallon, age of car, and gender. Miles per gallon is the dependent variable, and we want to use age of car and gender as the independent variables. Part A says fit the regression model, right? So let's do that. I'm gonna go to stat, regression again, fit regression model. Now the Y variable is miles per gallon. We have one continuous predictors, age of car. We also have a categorical predictors. Make sure you click on the box for categorical predictors, then you can see gender there, because gender is the categorical variable. All right. Now, since part C asks us to check the residuals, why don't we just do that right away? We're gonna go to graphs and click on 4-in-1 to get the residual plot. Now I'm gonna click OK to see my results. We've got the regression model, we've got the R-square, adjusted R-square. We'll also got the residual plot. So in the output, we can tell how this dummy variable is kind of created, and also the regression equations for both genders, female and male. And you can tell that for these two regression lines for female and male, the slope is the same, right? Negative 1.040. But the y-intercept is different. This is because we fitted two lines for female and male. Part B, interpret the least squares coefficient. And let's move to this table right here. It shows the coefficients that we need to interpret. The first coefficient we're looking at is negative 1.040. It's negative, meaning that when age of the car increased by 1 unit, when the car gets older, the miles per gallon decreased by 1.04 units, which makes sense, right? The older the car, the less mileage per gallon you can get. Probably something new for you is the coefficient for gender, which is 1.206. What does it mean? So this is the difference of miles per gallon between male and female. Now, since the output shows here this dummy variable is created for male, that means this dummy variable will take a value of 1 if the observation is a male, okay? And this takes a value of 0 if this observation is female. And that means in terms of the y-intercept, the male's y-intercept is 1.206 higher than the female's y-intercept, as you can tell from the two equations we have here, right? For male is 26.6, for female is 25.482. To a certain extent, we can interpret difference as the following: holding everything the same. For males, miles per gallon will be 1.206 higher than those for females. Okay, so this positive value suggests that the miles per gallon is 1.206 higher for males than for females. So I guess the data kind of suggests the other way, right? The question says, other things being equal, women tend to get better mileage than men, but the data shows the opposite. Since this interpretation for the coefficient for the dummy variable is kind of new for us, I want to type up the interpretation so that you have it on your record. So the interpretation for the slope coefficient for the dummy variable is that holding other things equal, mileage per gallon for males is on average 1.206 higher than that for females. Part C says, check the residuals. Do you see any assumption violated? Let's move on to the next page. So here are the residual plots. First thing we're going to check is the normality of the residues. To me, based on this part and this one, the two on the left-hand side, I can tell that this condition is not violated. So it's normal to me. The dots in this scatter plot are really kind of close to the straight line. So I would say residues are normally distributed. Now moving to this scatter plot on the right top corner, this is where we check for heteroscedasticity, meaning that the variance of the residues change over time. I don't see that either, although at least I don't see that condition seriously violated. The last scatter plot allows us to examine whether the residuals are independent, right? Whether there's any serial correlation. From what I can tell, there's no, because we can tell the residuals are randomly scattered. There's no pattern going up and down systematically. So we can tell all conditions are satisfied, nothing is violated. The model, at least based on the residual check, is good. All right, we didn't check for the fitness of the model or other things that we usually check. So I can't speak to other things, but based on the residuals, no conditions are violated. So that's all I have for this exercise. Let me know if you have any questions. Just feel free to email me if you need any help.